Okie dokie. We are live. Let me just double check we're live everywhere so we don't have any issues. Woohoo! How are you guys doing? I got my chat up this time before I got started with all of this. So let's see. Here we go. I'm live on YouTube. Fantastic. Let's see. Let's go check Periscope. Hello. Hello, everyone. How are you all doing? Hello, Bo. How's it going? How are you guys doing? I'm checking to make certain I'm live everywhere. I think I am. It looks like I'm on Periscope. Let me check on, well, it looks like I am on YouTube. Now I'm checking on Periscope. Yes, I'm live there. Woohoo! And I think I'm now live on Facebook and I believe on Twitch. So, hello guys. Yay, we're here and we're going. Fantastic. So this was, this particular topic was voted on by everybody. It was really a close freaking tie, man. I found it to be pretty interesting. And the thing that's really kind of cool about this is since I'm a chemist, I use a lot of the properties associated with light and electromagnetic radiation. And so it's something that we use all the time in science. Hello, hey Jesse. Hello Jade. Hello Nether. So today it's the science of photons and all about the electromagnetic spectrum. So let's go ahead and get started. Hello guys, woohoo! That's my really cool intro by Peter, also known as Gonna Go For It. So today we are talking about all things photons. So if you're not familiar, actually if you're not familiar with this type of format, essentially every single morning I put together these shows and it's based on a voted for topic by viewers. Essentially they give me different topics that they would like to learn about. I put it in a poll, everybody votes, then I wake up every morning and put together this particular show. Get that photon cannon. I've got a Nerf gun. You know, I do have a Nerf gun. I'm locked and loaded, ready to talk about photons. So what I thought I would do today, there's so much stuff we could talk about with photons. So I thought I would start more generalized and hopefully have a bit more detail maybe in another episode. I still would like to do a show called the master class, to where we're digging more into the harder aspects and more difficult aspects of science. Hello, Spooky. Hello. So what are we going to talk about today? Well, we are going to talk about what they are, what they do, where we can find them essentially, and how we use them. We use photons for so much stuff. We use it for light, of course. We use it for solar panels in order to collect energy, and we can get that energy through the photoelectric effect. We're going to talk a bit about that. We're going to talk about the different types of spectroscopy. We're going to talk about how it is that we have a visible spectrum and what happens when we go outside of the visible spectrum. What exactly do those particular rays do to atoms and bonds? So we're going to talk about all of these different things today. So if you were here do photons interact with the Higgs field? Well, the Higgs field is how matter is carried. You would think that photons would interact with the Higgs field because photons do interact with matter in various type of ways. So something that's very interesting about photons is they are both a particle and a wave. So when you try to observe a single photon, you don't really realize that it's still moving and it's still part of a wave, but it's also a particle. It's what we consider the basic unit of electromagnetic radiation. Now, this particular term, photon, was coined by Gilbert Lewis in 1926. Hello, Christopher. Hello, Omo boy. How are you guys doing? I think I saw somebody with barbecue earlier. So we're talking about photons. Like it'd be cool if we had like the Star Trek photon torpedoes. Oh, I have the Enterprise somewhere in my background. It'd be interesting. Hello, Cap. That's Higgs boson, not Higgs photon. I believe photons are part of the boson type of family because it does carry energy. It doesn't carry matter, but it can interact with matter. Good morning. So we're talking about we're going to talk about what it can actually do when it interacts with matter. So what's a cool thing about photons? Well, they move at the speed of light. Duh. It is actually light. So that's always kind of funny. When people are like, do photons move at the speed of light? Yes. We are shedding light on this subject. You can shed light if you are fluorescent or phosphorescent. And I'm going to talk about how that happens too. Oh my goodness. So photons move at the speed of light. Who'd have thunk? It's traveling light. They're considered electrically neutral. They have no mass. They do have momentum. And that's something that I didn't put together in this particular PowerPoint. We should talk about at some point the effect of gravity on photons. Now, gravity usually affects mass, but the thing is when photons are in motion, they have momentum. So that's kind of like how you can kind of bend your brain around that, to where gravity can affect the momentum of the photons. So it can pull on that. Yes, photons will sometimes entangle with each other. I believe so, yes. Your joke wasn't that bad. Give it back, I want a sunny day. Oh my goodness. So they do have energy, but not when they're at rest. The energy is generated from the movement of the photons. They can be created and they can be destroyed. And this is through their particle interactions that they have, especially with matter and electrons. Hello, hello, another freaking atheist. Oh, wait a second. So I'm going to go to like solo here. Because you guys don't need to see my script. Don't you just love it when I sit there and I accidentally put up my script slide and you guys are like, wait, what's she going to say? Oh, this is the first one you're here. Yay, Christopher, I'm so glad you're here. This is awesome. I'm trying to see if I can shift it to a later time if that's easier for other people, but I do have people on other parts of the planet, so it's hard. I am doing well, thank you. So essentially, what are we dealing with photons? Well, they carry energy based on the distance between waves. Okay, so we have photons are both a wave and a particle, and so when they carry their energy based on the distance between two waves. And I'll get a bit more into that in just a bit. Now, the shorter the wavelength, the stronger the energy. This is why certain types of radiation like UV, gamma, and X-ray are bad for us. Those wavelengths are short and the energy increases. So photons, as I mentioned before, can also be created and destroyed. Oh, it's 8:16 a.m. there. Woohoo! In regard to creation of photons, this happens when something emits electromagnetic waves. You can emit photons in certain circumstances. In their destruction, they can be absorbed by matter and transfer energy to the atoms and molecules within that matter. creation and destruction of photons, but however, must obey the laws of conservation of both energy and momentum. So if we have, I'm going to do a little example here. So if we have Iron Man and Silver Surfer, Silver Surfer, they'd be alloys, not allies, right? So let's pretend Silver Surfer is a photon coming in, and it goes, well, let's say that Iron Man is on a surface. We'll say he's on a surface, and Silver Surfer hits this surface, and Iron Man is an electron. Well, two things are going to happen. He's either going to absorb that energy and throw Silver Surfer off, or, you know, if he hits hard enough, he's going to spring off the other side. This is where we're talking about both energy and momentum. Even though photons are destroyed, that energy and that movement still has to continue on and be conserved. How? What do you mean now? Oh. All right. So that's what we're talking about with photons. I'm trying to catch up on the chat because I've gone through. Oh, you've been sad to see many live chats. And you've been thinking about the last one. Well, if you're curious and you want to learn more about these different types of particles, one thing you can do, I actually did an episode on subatomic particles, and I talked about the Higgs. I talked about the Higgs field. I talked about leptons and quarks and all of the cool things associated with them. So there you go. Iron Man is the only one projecting photons that we can see, that is. Yes, he is using electromagnetic radiation in the form of, you know, like very, I guess, condensed electromagnetic waves. It'd be really kind of suck to be hit with gamma radiation from Iron Man. The trick of the light, though. You came here to get your sunlight back. Well, it's currently outside and it's really hot right now. Something people get confused about, and I kind of want to address for a second. Photons generate heat because of the effect that they have on electrons and the different ways that they cause these atoms to move. And I'm going to talk a bit about what they actually do with the atoms. You have vibrational, you have rotational, and then you have all-out breaking of bonds. So that's kind of what photons can do. So when you're moving these electrons around, and that's why metal heats up when you light it up, because those electrons start moving and that movement generates heat. We all know DC is better than Marvel. So light in itself doesn't have heat on its own. The electrons it interacts with, that generates heat because it causes those electrons to be excited. Hello. Hello, everyone. Hello, Owen. Hello, Kirk. So that's kind of what we're talking about today. So now we're going to get into something that's going to freak some people out. Math! Math! Math alert! So we've been talking about energy. We've been talking about photons generating and carrying energy. Back to me, woohoo! So we're talking about photons and their effect on other atoms and molecules. So where is the math in this? Well, sometimes math is kind of important for you to understand how energy is carried with photons. The photoelectric effect. Oh, goodness. Wonder if anyone won a Nobel for that. They did. And it's something that people don't commonly associate with that particular scientist. Yay! And so the energy, to determine the energy associated with photons, you have energy is equal to H times F. Well, H is a constant. It doesn't change. So it's the same number every time. So good news on that. Frequency. So you have Planck's constant times the frequency is going to give you the energy associated with that. Now, if we want to take the frequency, how do we determine that? Well, we take the speed of light and we divide it by the wavelength. The wavelength is literally the length in between two waves, all right? So if we have a wavelength let's pretend that Silver Surfer and Iron Man are roughly the same height. Now they're waves in this case. Now if we put them closer together, they're going to be far more powerful. They're further apart. They're not as helpful in a fight against a lot of baddies. But, you know, we put them back to back. They can take out all sides, right? So the lengths between the two of them, that's the wavelength, right? And so if we measure the wavelength, and we take that, and we take the speed of light and divide it by the wavelength, we get our frequency, right? We get our frequency that way. And that's all multiplied by Planck's constant, and then we get, boom, energy. Energy is fantastic. So, so that's what we're doing with that. So let's take a look at how this is. Let me make certain I'm covering up some of this graphic. I really need like a separate little scene to where I don't cover up stuff so much. You know what I mean? Math is, you know what, I really didn't, and I'll be honest, here's a little side note about me. I absolutely hated math for a long time because I didn't quite understand it, and it took me, it came a lot from the teachers that I had. I just couldn't wrap my brain around it. And when you took science and mix it with math, you get people that freak completely out because, like, science is hard as it is, now you're throwing in numbers, and people freak out. But for me, what made math make sense was applying it in a practical application kind of way. So, what about his cat? Oh, the frequency. Oh, goodness. Okay, so here we have examples of long wavelengths versus short wavelengths. And some people, you know, and for some people, they're like, well, if it's longer, that should mean more energy. No, 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 no. That's the bigger the wave, the stronger. No, 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 no. That's wrong. Don't get that wrong. The shorter the wavelength, the more pow you get. So the shorter the waves, you know, like the wavelength in between the two, the more pow you're going to get, the more bang for your buck. I'll give you a more practical example for that. So essentially how we determine the energy is by measuring in between the wavelengths. You get a long wavelength versus the shorter wavelength. So yeah, so there we go. Like the length of the waves. The shorter, like pow, the distance. You want them closer together so you can generate, you know. So it's much harder to get. I hope I explained that right. I might not have explained it so well. So you want shorter wavelengths. You don't want them longer. You want them shorter, more spiky. You get the frequency compacted, more bang to your buck. Hopefully that makes sense. So when we're talking about this, let's talk about the math a bit. So we've got the E equals H times F. H is the Planck's constant and F is the frequency. Planck's constant is 6.626 times 10 to the negative 34 joules per second. Joules times second. That's a universal constant. Now the energy of each photon is inversely proportional to the wavelength. So the shorter the wavelength, the more energy the photon carries. The longer the wavelength, the less energy the photon carries. Frequency is how many crests of the waves that pass over a point in 1 second. So we have our frequency, all right, so if we've got our Iron Man and our Silver Surfer, let's say that they're about the same width, so that's our wavelength. We move them closer together, that's our frequency. Okay, I think I got that a little bit backwards earlier, so I'm correcting myself. I am not infallible. So let's say Iron Man and Silver Surfer are kind of tall and slim, all right? And then the closer we put them together, the more bang for your buck. The further they are away, the less effective they are, especially if they get wider. So, yeah. It sounds good. If a spring is highly coiled, then it will have a high level of energy it releases when it can vibrate. Yes, that's another example. Here's another example for you. So let's look at frickin' kangaroo science, right? Okay. So to kind of put this in another way. If you're still confuzzled about thinking bigger waves should mean more energy, let's look at kangaroos, all right? Which kangaroo is exerting more energy? The top, of course. More waves in a shorter period of time mean more energy. And And the smaller the waves are, the shorter the length of the actual waves. And the closer they are together, that's the frequency. Closer they are together is frequency. The shorter the actual waves means you're going to exert more energy. Let's see. Aren't cosmic rays a collection of radiation that include gamma rays? Well, that's an interesting question. What my understanding is, they're pieces of atoms. Cosmic rays are kind of like different particles all collectively together that go blasting at something. So there are lots of different things. So it'll have some spring in its step. Yes. So that's pretty cool. So I like this graphic because sometimes people have a hard time. They're like, bigger means better. Not necessarily. Not in wavelengths. That's not good. It has less energy. You want more bang for your buck. And so here, now we're looking at actual different wavelengths. All right. So we have our shorter wavelengths and a higher frequency. And so which one is going to have more energy? The bottom one. That do. It's like if you're dealing with a person that's really tall and they take one giant step, and then you have a shorter person and they have to take like 10 steps to match that one big step. That uses more energy. Oh my goodness. So here we've got just kind of more of a visual example of the different types of wavelengths you can come across. Are there any wavelengths shorter than gamma rays? I missed that question. I'm not entirely certain. I think that might be, if we're talking about on the electromagnetic spectrum, that would be no, not to my knowledge. If we're talking about rays in general, you probably can get shorter rays through like the cosmic radiation and that sort of thing. I would think you could have like shorter wavelengths with that. But I'm not 100% certain. But that's a really good question. I kind of want to find out now. That sounds pretty groovy. But as far as on the electromagnetic spectrum involving photons, it doesn't get any stronger than gamma. And to be quite honest, if we all exposed ourselves to that, we wouldn't Hulk out. We would just probably fall to pieces because it actually breaks bonds, depending on the amount of gamma radiation you get exposed to. Now we're looking at the actual spectrum. So as we move across the electromagnetic spectrum, we increase the frequency, thereby increasing energy. This translates to what we know as microwave, infrared, visible, ultraviolet, X-rays, and gamma radiation. We use photon energy in just about everything we do in life, as well as many facets of science. Alpha particles, electrons, positrons, protons, neutrons. Yes. So when you're talking about, so I'll pop you guys up over here. So when you're talking about cosmic radiation, you're talking about bits of just about everything involving subatomic particles, elementary particles, that sort of thing. And that's highly condensed and blasting at things. So if we're talking about that kind of radiation, I think those wavelengths can be much shorter than gamma rays. I'm not 100% certain, but there you go. I'm not exposing you to gamma rays right now. I'm exposing you to visible spectrum rays, not infrared and not ultraviolet, because we're eye safe here. So it's okay. So that sounds correct. Oh, getting hit by gamma rays. Yes, that would most likely vaporize us. Over a period of time, gamma rays essentially destroy bonds between, even covalent bonds. So we're made up of a lot of covalent bonds through proteins and DNA, DNA, but mostly what we're walking like proteins, okay? So if we blast our covalent bonds with gamma radiation, I showed gamma rays, let's see. Here we go. Hey, here we go. You guys know Marvin the Martian right here. A rhodium Pu-36 explosive space disintegrator. I would think that if he had, this would probably be some gamma radiation right here. There we go. I'm so glad you guys are enjoying these lessons. Yeah, so yeah, we couldn't, if we had Marvin the Martian, this is actually a pin, if you're wondering. This is one of my favorite things I've had for an extremely long time. This was made in 98. Warner Brothers 1998. I guess got a little, there. But essentially, if we had gamma radiation coming out of this, it would actually break bonds. So, and you're talking about, it's a space modulator, yeah. Explosive space. It says disintegrator on here, but I believe you said space modulator on the show. But yes, gamma radiation is not fun for to be exposed to. It is used in various types of cancer treatment, but in medicines, small amounts of medicines, not all over necessarily. They're not blasting people with gamma rays all over, not like you would, like an X-ray or something. It's quite different. So there we've got that going on. So let's hop over to something really awesome called the photoelectric effect. Hence the name ionizing, ionizing radiation. We're going to talk about the differences between the two as well. So Einstein, most people are like, oh, that's the general and special relativity guy. That's the dude that was all about E equals mc squared. But what's very little known about him, well, not little known, it's not as common knowledge as like the general relativity thing, is that he won the Nobel Prize in 1921 for showing that photons can actually kick electrons out. So essentially, we can actually eject electrons through introducing light. All right. Okay, well, I hope you get your internet fixed. AF. Have a super awesome Saturday. So here is an example kind of the photoelectric effect. So we have an incoming ray of light, so here we go. We got Iron Man, and this happens on metals. So we have Iron Man sitting here, and we have this incoming ray of light, and it just, boom, it hits the surface, and then Iron Man is our electron in this case, and he goes ejected out. Well, depending on the frequency of the light, not all frequencies work, but depending on the frequency of light and how much energy is compounded into this metal that Iron Man is sitting on is going to determine how fast he moves as well. Kind of makes sense, doesn't it? Because we have to have that continuation of energy and that conservation of energy and momentum. So however much you put in, that's going to have to be absorbed, and in the photoelectric effect is released by ejecting electrons. So that's kind of what that does, which is really cool. Photons are just bullies. They can be. So here we have some scary looking numbers that people might freak out. But here we've got potassium. So what we need is about 2 electron volts in order to get an electron to be kicked off. So in this case, if we need about 2 electron volts, if we blast potassium with about 700 nanometer wavelength, okay, it's about 700 nanometers on the actual length of the wave. We blast it with that, it's not going to happen. So we can sit there and shine a flashlight on some metal, but we're not going to have ejection of photons, especially if we need much shorter wavelengths. For instance, 550 nanometers. That's going to be the good wavelength to be able to eject an electron because it can generate 2.25 electric volts. So, and that velocity is also going to be associated to how fast those electrons, that velocity is associated to how much energy is put into the metal. So the higher the energy, the faster the electrons will be ejected. So if we move from 550 nanometers, remember, when we go smaller wavelengths, that's higher energy. That means those electrons are going to go and be flying right off of there. And it's almost threefold at this case. So the thing that makes electrons really cool in this regard, and the why is it metals, is because metals have electrons hanging out on their outer shell that can easily pop off and come back on. This is how we have electricity. This is why metals are good conductors, because they're able to pass those electrons back and forth pretty easily. So that's why we also call it the photoelectric effect, because we're able to displace, eject electrons, and bring them back. Yes, it's not the intensity that has an effect, but rather the wavelength. The wavelength is exceedingly important. It's the energy. And since the energy is associated with shorter wavelengths, that means more energy means you're going to have a greater chance, a greater ability to eject electrons. And more energy means those electrons are going to move faster. So, you know, I was kind of one of those people that kind of had to wrap my brain around the idea that shorter wavelengths were, you know, higher energy and higher frequency. So it's just like, you know, being able to wrap your brain around that was something that was kind of difficult for me. But the thing that absolutely kind of made it solid for me was being able to understand it and applying it in what we call spectroscopy. So I'm going to talk about spectroscopy in a bit. Okay, so Nat Sel looked it up. The shortest wavelengths measured and hypothesized are called ultra-high energy gamma rays. Well, cool. So they've been hypothesized. Have they actually been found yet? Because that would be pretty interesting to find out if they've actually found those particular rays. Oh goodness, I'm still drinking my coffee this morning, and it's 10:39. I've been up since about 6. Okay, so as scientists, we use the photoelectric effect for many reasons. So one thing that we do is we can use it to determine the composition of samples as well as the concentration of different compounds in a sample. So I'll give you an example. Something that I used to do a lot of in the job that I just left recently. My last job, we use light from a certain wavelength. For example, in this case, it was 280 nanometers. When you show that through a tiny cuvette of a solution, the amount of protein can be determined based on how much light is absorbed by the sample. So this is called absorbance. So if I have a whole bunch of little proteins, so this is like my dice bag, all right? I'm a nerd. I have a D&D dice bag. I actually have a D20 that lights up when it lands on 20. So if I have all of these, let's say all of these are different proteins, they're going to absorb light at 280 nanometers. So if I have a solution inside a cuvette and I want to know how much protein is there, I can blast it with light. However much is absorbed is going to be linked to how much protein is in there. That's the concentration. Another use for this type of effect is called fluorescence. So this is our glow-in-the-dark stuff, and phosphorescence. Electrons can get excited to higher energy levels. And so let's say Silver Surfer and Iron Man are friends, all right? So let's say Silver Surfer, because I've been using Silver Surfer as photons and I've been using Iron Man as electrons. So let's say Silver Surfer and Iron Man are friends. And then we have, this is a fluorescence situation where you've got, hey, look, here comes Silver Surfer. So at a certain wavelength, you have absorbance and they're hugging each other. And Iron Man is like so excited. He's like, I'm going to go fly around. Woo, we're friends. We're hanging out and stuff. So they're super excited. Well, after a while, you know, you kind of like, I'm tired. So it's good to see you, buddy. And then he relaxes down to back a normal energy state, you know, resting energy state for this electron. And then Silver Surfer's like, see you around, man, and continues on. He's emitting these photons. That's essentially what fluorescence and phosphorescence is. An excitation of an electron that absorbs a photon and then it lets it go. Now, we can use fluorescence and phosphorescence to determine and quantify how much of a particular compound is in there. So electrons get excited to that higher energy level. When light's absorbed, they move up to the higher energy level. And then when they relax, the light is emitted. That amount of light emitted can be quantified to determine how much of a compound is in a sample. Now, because of the light emitted, and also another cool thing, ultra high energy gamma rays. Let's see. Okay. I'm trying to catch up. Take pride in your inner nerd. Yes. And I am on Discord too. So up to 10 negative 20 meters have been measured. Anything shorter has only been hypothesized. Got it. All right. Thank you, Nether, for that information on the ultra gamma rays. Cool. All right. So another thing that's really cool about the spectrum is because of the light emitted from other planets, we can also determine what their atmospheres are made of based on the wavelengths and the spectral lines that we see. So now I'm going to show you some cool stuff. Some really cool stuff. So here, dun dun dun, we have what is called spectral lines. These are spectral lines, as you can see, associated with hydrogen, helium, nitrogen, oxygen, argon, neon, xenon, and mercury. So why are spectral lines cool? Spectral lines are pretty cool because we can get them through emission or absorption of light. And so we have both emission and absorption spectral lines. Now, how can you tell the difference between emission versus spectral? And how do scientists use this? Well, they can take a prism, and certain light that comes through is going to give off this particular type of emission line. So these spectral lines that we see. So we're able to determine what the atmospheres are on other planets because of that. Yes, Doppler shifts. I'm going to talk about Doppler shifts here in just a second too. Actually, I think on the next slide. So when measuring photon wavelengths from far distances, you do have to account for Doppler shifts. So you guys are so smart. I'm going to talk about that in a little bit. So how can you tell the difference if it's an emission, if it's actually being emitted, or if it's being absorbed? So here at the top, this is emission. So everything else is black behind it, and there's specific colors that are very thin lines. We know that's emission. Absorption is going to be the other way around. We're going to see all of these other colors with different little black lines kind of stuck in the middle. So we know that emission means that those electrons were released after, those electrons released photons after they relaxed. Absorption means those electrons are holding on to that energy and the rest of the light is passing through. Now, spectral lines of a specific element or molecule at rest in a laboratory always occur at the same wavelengths. For this reason, we are able to identify which element or molecule is causing the spectral lines. Now, when we're looking at the spectrum of other planets, we do have to take into consideration the Doppler shift. So let's talk about red shift and blue shift. How cool is that? Red shift and blue shift, guys. So yes, Immutable Destiny brought this up about Doppler shift because when they're moving, it's a bit different, and we have to take in consideration this movement. So if the emitter or absorber atom molecule is moving, so if astronomers are looking at light that's moving from other planets, the position of the spectral lines will be altered via the Doppler shift along the spectrum. You can have what's called a red shift or a blue shift. A red shift means the lines move to longer wavelengths. which means they're going to move the other way up the spectrum to where the wavelengths kind of lengthen out. Therefore, an emitter or observer therefore this emitter or absorber is moving away from the observer. So they're moving away, so those wavelengths are going to kind of lengthen. The blue shift means the lines move to shorter wavelengths. This means that the motion this is moving towards the observer. We can also use red shift and blue shift in determining changes within a solution. For example, the binding between two compounds. So I've done work in UV vis spectroscopy for the cancer test that I helped generate in graduate school when I was working on my second master's. We determined whether or not there was binding between our antibodies and our nanoparticles if there was a red shift. So it would move to the left on the spectrum to the larger wavelengths. So you can use red shift moving to the left on a UV vis spec, or moving to the right on a UV vis spec, that's blue shift, to the shorter wavelengths in order to determine whether or not you had binding. Or is it the other way around? Depends on the which way your UV vis is measuring. So if your longer wavelengths are to the left and your shorter wavelengths are to the right, you can determine the shift based on the measurements of the wavelengths. I hope I didn't just confuse everybody. Hello, crocus squirrel. Purple rain. So you have red shifts and blue shifts. So those are also useful not only in, the movement away from you, if it was moving away from you or towards you, but also to determine whether or not you've had a reaction or binding between two compounds. There's lots of different things that scientists do using red shift and blue shift. Yay! I'm so glad this makes sense. Red rum. Oh goodness, are we talking about The Shining now? Hello everyone. So a little bit of an example of stuff. So I'm gonna pop over into the corner here so you guys can kind of see examples of what I was talking about with spectroscopy. So we have the different types of electromagnetic radiation that's absorbed by different compounds, how that energy is used, and the type of spectroscopy associated with that. So UV vis, you've heard me say UV vis, UV vis. We use that a lot for spectroscopy in order to determine whether or not certain compounds have interacted with each other, whether or not there's what the compounds are based on the absorbance at what particular wavelength. Also, you can determine the concentration of a certain compound by blasting it at a particular wavelength, like 280 nanometers for standard proteins. That's because of the aromatic rings that are on there. That's what picks up at 280. So what this essentially does is it moves electrons to higher energy levels. Now, infrared, this vibrates bonds. So you'll have Iron Man, maybe Iron Man, and well, no, I've used them for something else. So essentially, if you have two things that are bonded together in covalent bonds, infrared infrared rays essentially vibrate that bond between the two. And we can use this on infrared spectroscopy. So whatever wavelength is shaking that particular bond, that's going to be indicative of certain types of compounds, to where they will only, have that vibration, that vibrational movement will be associated with infrared. Microwaves, this rotates molecules. This is essentially what heats up your food. So when you blast food with microwaves, when you're trying to cook it, it's rotating water molecules. And so that gets them moving around. Remember I said light itself doesn't heat up anything by itself. It's that movement of molecules and electrons that generates heat. This is how things cook in your microwave, and this is also what they use in microwave spectroscopy. Radio waves. This changes nuclear spin, which is also called nuclear magnetic resonance spectroscopy. NMR, nuclear magnetic resonance spectroscopy. So when you're dealing with radio waves, it can actually change the spin of the nucleus. So this is what we're dealing with when we're talking about different type of spectroscopy that scientists use to determine composition as well as concentration of different compounds in samples. Blasting food, I thought we cooked food. Now explosives are used for destroying things, not for cooking. Well, you know what? Electromagnetic radiation can absolutely destroy things. So it depends on the frequency as well as the wavelength. So the shorter the wavelength, the higher the frequency, the more power, and boom, you're ripping apart compounds, Don't necessarily want to do that all the time, I suppose. So here, now we're getting into non-ionizing versus ionizing. And now I'm tiny, so I'm going to make myself big again. Here we go. Boom. Through the magic of technology. So what do we mean by non-ionizing versus ionizing? So I just talked about infrared thermal and how we have rotation of molecules and how we have vibrating molecules. That doesn't completely destroy the bonds, does it? You're just moving it around a little bit, getting a little bit of energy that way. When we're talking about ionizing, we're talking about actually breaking bonds. Hydrogen bonds, talking about breaking hydrogen bonds. That's what holds your DNA together, hydrogen bonding. It's not covalent bonding. But we start out with hydrogen bonds, and then we go on further down to actually breaking covalent bonds. Covalent bonds, single and double bonds, to where two molecules are attached together. And so when you're dealing with that, you're actually breaking the bonds that way. That's really bad if you're a human and you get blasted with gamma radiation on your skin. Then your proteins are falling apart. So you don't want that. And so we're moving along this. So ultimately, this is why we see people who are exposed to heavy amounts of X-ray and ultraviolet radiation suffer cancer, because cancer essentially is damaged DNA. If you damage your DNA, you increase your risk of cancer. So that's something to kind of consider when you're talking about non-ionizing versus ionizing. Non-ionizing, we're just vibrating bonds, we're just rotating them a little bit, we're not destroying the sample. If I were to blast my protein sample in my solution with gamma rays, I've ruined my protein. Sometimes that's useful, and you can know, oh, well, these are all the different things that made up my protein. Sometimes that's not so useful, and that's a bad idea, especially if you intend on using it later. That's why there's different types of electromagnetic radiation that scientists might use in regard to determining composition of a sample. If you're fine with breaking stuff apart, you can use shorter wavelengths and higher frequencies. If you don't want to destroy your sample, then you want to go with non-ionizing techniques, where you just shake it up a little bit, but not completely obliterate the thing. So that's the difference between non-ionizing and ionizing radiation. Who'd have thunk, right? The peculiarity of alpha particles would have been interesting too. Yes. Well, alpha and beta particles. I'm almost at a full hour. There's so much we can talk about. I talk a lot about subatomic particles in another episode. So if you want more information about that, you can, X-rays are used in analyzing protein structures. Here we go. I'll pop this up. But it takes prepping and the proteins don't survive it. Yes, that's true. You can do that. You can, and there's also you can analyze protein structures by how they break apart with different types of radiation on there. So you can you can also determine, like with mass spec, you're essentially breaking apart a molecule, and then you can kind of determine how it's pieced together through using mass spec. And also other types of spectroscopy, because you're going to have breaking patterns that are indicative of certain types of proteins on how they're put together a certain way and how they break apart. They tend to break apart similarly. So when you go blasting your protein with different types of radiation, they're going to break into parts kind of the same way each time you do it. And so there's actually a database. This was one of my qualifying exams when I was finishing my master's. It was all about mass spec. And so there's a whole database that's there that has the breaking patterns of different compounds. It's not 100% exact, but it's pretty freaking close. And so at least gives you kind of a jumping point to find out, the structures of your proteins based on blasting it, and breaking it apart through mass spectroscopy. Yes. Ingesting rather than not digesting. I missed something there. So, I missed something. Okay, effect on skin versus actually ingesting alpha active material. I will look up on some of that, and I can add that to a list of topics to do. So, gosh, I'm almost finished with our chat. Guys. So we want to limit our exposure to the types of ionizing radiation because of the fact it can cause cancer. So one last little bit on visible spectrum. So, yes, please. Sweet. I will add it to the list. So what we're dealing with on this, let's see, last little bit. Our eyes are only, why do we have the visible spectrum? All right, well, our eyes are only receptive to a range of wavelengths within this spectrum. We have our rods and our cones. And so those are able to absorb certain wavelengths. The higher frequencies, though, as I mentioned before, can actually damage your eyes as they can break bonds and damage DNA. This is why we take measures to be safe in our dealings with electromagnetic radiation. So this is why we wear sunglasses, and we're trying to limit our exposure to harmful types of ultraviolet rays, which can actually cause all kinds of problems for our vision. And so, it's a flat hour, man. There was so much information here. We have talked so much about photons. We've talked about what they are, what they do, where we find them, how we use them. We use them for so many different things. We use photons in our microwaves. We use them for light bulbs. We use them in our solar panels. We use them for all kinds of different things. Yes, human vision is pretty limited compared to other animals. That's true. So we've talked a lot about all the different ways we use the properties of photons and its effect on matter and how it can interact and break apart bonds. It can excite electrons, causing electrons to even emit photons as well through fluorescence and phosphorescence. We've talked about so much stuff here. I don't know if it's just me or did this show seem a little light on content. But oh, goodness. I didn't get into a lot of the uncertainty principles. There's so much to talk about. So when somebody was like, I want to learn about light, I'm like, well, that's a pretty hefty subject right there. Yes. So, oh, goodness, wrong one. There we go. We got the chat there. So, chaos theory. Photons are emitted when electrons jump from higher to lower energy levels, the energy states in case of black body radiation. Goodness. Yes, eyewear with 100% UV protection. You absolutely want to do that. I'm going to take a moment to show you all of my sources. But you can go to my website. There's so much freaking information to go there. There's so much information on my website on ScientistMel.com. You can go there and check out all of the sources that I used. I got my images from Google search, but I put all of my slides are on ScientistMel.com/resources. It's where this isn't genealogy kits. Look at that, man. Dude, I didn't change the title. See, you know what? I'm gonna start putting typos in my slides on purpose and see if anybody notices. And then I'll just shoot them like 5 points for Gryffindor or whatever, or for Slytherin. My house is Slytherin, but there you go. So it's just like, I didn't change that because I'm a silly person who does silly things sometimes. Yeah, so there you go. But I'm going to say thank you to my awesome patrons. They help me keep the lights on. I'm bringing back my audio podcast, and I'm working with somebody, a scientist named Ashley. And so it'll be us talking all about the different things associated, all the sciencey things. So Tony, James, Lauren, Jen, Carl, Melanie, Patrick, Daniel, Stephen, Paula, Tim, Carrie, Cersei, Keith, Duke, James, Andy, Zachary, Tony, Bo, Stephen, Sarah, Chris, Graham, Dragnot, Godless Iowan, Jennifer, Corey, and Heavy. Thank you for helping me keep the lights on and helping me do what I do. My patrons have their very own show that I tried to live stream and it just wasn't working out. So now I pre-record these shows. It's called Science Sunday School. Every Sunday, I have a little miniature 10-15 minute video talking about the latest and greatest in scientific findings for current technology. So please do check it out. And my pledges start at just $1 a month. If all of my Twitter followers gave me $1 a month, this could just be my job and I could travel to people's cities and do talks. And I am also hoping to reach a point to where I can have a science communicator convention to where we can bring all of the science communicators together and to incorporate that into boosting scientific literacy and being passionately curious again. Goodness. So, where can you find me? Everywhere. I'm everywhere on the internet. ScientistMel.com, Patreon, Periscope, YouTube, Facebook. I'm also on Twitch, and I have a Discord. So ask me questions, and if I don't know the answer, that's okay. I can phone a friend from time to time and ask them what's going on with that. What caused the electrons? That's an interesting question. I talked about subatomic particles on another episode. You can pop over there and take a look and see if that answers any of that. But I do have a lot of information there on that particular episode. And yes, use hashtag HeyScientistMel on Twitter for questions. And I'll be happy to answer them. This has been awesome, guys. You guys have been like really, really freaking cool and engaging and talking and stuff. I do have an announcement a bit later. Once I get that all finalized, I'll be able to share it with others and let you know. So you'll have to look out for that. It's a shift in my working and what I'm doing. So that's cool. What caused subatomic particles? Have a look at what I discussed on the science of subatomic particles, and let me know what you think. And if you have other questions, if you have questions after that, hit me up and let me know, and I'll be happy to answer them. And if I don't know the answers, guess what? That's okay. I will find the answers. And I will phone a friend sometimes. So that's the thing that happens. I have really awesome science friends that are just like, yeah, let's talk about it. Yeah, this is the answer. So it's just kind of what you do, and that's kind of how science is. So thank you guys for being here. This has been super fantastic. I'm so excited. I'm so glad you're here. So have a fantastic Saturday. And I will see you guys later. Bye. Thank you for being here. Like, subscribe, and share. Help me out. Help me spread the good news of science. Have a good day.